So we want to solve this 2 by 2 system, and we definitely have tools. We can set up an augmented matrix and use row operations to solve it. But we want to turn this process into something a little bit more algebra-like. So first, let's look at an operation and see what happens. If I were to take the coefficient matrix, 2, 2, negative 1, 3, and I'm going to multiply this by the column matrix xy. Now, it might not seem obvious to you why I would do that, but I want to look and see where this goes. If I do that, I get 2 times x is 2x minus 1 times y. I guess I don't need the 1. And then the second row, 2 times x is 2x plus 3y. So really what I ended up with when I take the coefficient matrix and multiply it by the variable matrix, I end up with the left-hand side of my system, which is kind of cool when you figure we can take the same thing, or we can take what the coefficient matrix times the variable matrix and just set it equal to the constant matrix. So I've really sort of set up an equation, one equation that describes this entire system, which is very, very handy when you think about the fact that this can now be written as matrix A times the variable matrix, remember the variable is the thing we're solving for, equals, and we can use B for this, the constant matrix B. Well, if this was just simple algebra, I would divide both sides by A, getting that the variables in this system are equal to B divided by A. But as you know, we don't really have a way to divide one matrix by another matrix. But we do have a way to rewrite divide by A. This is really just the same thing as 1 over A times B. And 1 over A, this could just be written as the inverse of A times B. And you have to be really careful here. It is always written x equals A inverse times B. Your matrix multiplication is not commutative, and it matters which direction you multiply. And we're going to multiply in this direction every time. Okay, so let's go ahead and solve this system then using this information. First thing, let's set up a coefficient matrix, 2, 2, negative 1, 3, times my variable matrix equals 1, 13, the column matrix, 113. So really all I've done is turned my system of two equations into really a simple algebraic function or process. So that means I want to multiply, or to solve for this, I'm taking matrix A times the column matrix X equals B, which means I want to multiply to find X, A inverse times B. Now all I need to know is what is the A inverse. We have a couple ways to do this as well. I could set this up to negative 1, 2, 3 with the identity matrix, do row operations to convert my coefficient matrix into the identity, and it will automatically convert my identity into the solution or to the inverse. But we don't really want to do that. What we want to do is use the determinant because it's so much easier, especially in a 2 by 2 matrix. So first, let's determine the determinant. That's 1 over AD, so 2 times 3 is 6 minus 2 times 1 is negative 2. 2 times negative 1 is negative 2, so plus 2. Times, remember, the flipped opposite matrix. So I'm going to flip A and D, and I'm going to take the opposite of 2 and 1. They stay in the same place, but I just changed the sign. So now I have a simple scalar, 1 over 8, 1/8 times 3, 1, negative 2, 2. That gives me 3/8, 1/8, negative 1/4, and 1/4. I don't really like getting all those fractions. I could multiply by another scalar to get rid of them, but I'm not going to, or at least to make them less ugly. But I'm not gonna. I'm gonna keep working with it. So we know that this is the A inverse. All I have to do now is multiply 3/8, negative 1/4, 1/8, and 1/4 times our coefficient, oh, our matrix B. So 1 times 3/8, 1/8 times 13, so that's 3/8 plus 13/8, and negative 1/4 plus 13/4. Well, 13, 14, 15, 16/8 is really just 2. And then 13 take away 1 is 12, divided by 4 is 3. So even though I had those ugly fractions, I ended up with the solution, x equals 2 and y equals 3. So that is one method for solving a system of equations using inverses. There's another one, and it's called Cramer's rule. So using Cramer's rule is much less like using algebra and much more like magic. Of course, we know it's not really magic. And let's look at what we need in order to carry out Cramer's rule. Well, the first thing is we want to be able to write the determinant of our, first thing we're going to need is a system of equations. So let's create an arbitrary system of equations. AX plus BY equals E, and CX plus DY equals F. So we're going to need the determinant of A. And in this case, the determinant of A is just going to be the determinant of the coefficients. And then we're going to need a determinant matrix that we call A with a sub X. So the determinant with the sub X is what we're going to use to solve for the X term, or the value of X in this system. And the determinant for the sub X is using exactly the same determinant that you already have for all other variables except for X, and we're going to replace E and F for X. So see what happened there? Is for determinant sub X, I'm going to not use AC, which is part of the X variable, and I'm going to use EF instead. And then the determinant of Y, the determinant sub Y. Wow, I'm having a hard time writing that. A sub Y determinant. There we go. And it's exactly the same thing. We're going to keep our X coefficients, and we're going to replace the coefficients of Y terms with the constants. Okay, that's all we need. Those three tools. Easy to find, obviously. If A, B, C, and D are just numbers, it's just a matter of putting numbers in. So let's go ahead and solve one. Oh, we're not done solving, actually. And so the rule, I haven't explained the rule. To find the value of X in this system, all I'm going to do is take the X determinant and divide that by the determinant of A. I so want to make my A like a triangle today for some reason. All right, so we're going to take to find X, we want the X determinant divided by the determinant of my coefficient matrix. To find the value of Y, we want the AY determinant divided by the A matrix, the determinant of A. Okay, so now let's do an example. We want to use Cramer's rule to solve 4x1 minus 5x2 equals negative 49. And then we want to solve negative 3x1 minus 2x2 equals 28. Now, I used a little bit different notation here. I have x1 and x2 notation. This is really common in linear algebra because we're not dependent on good variables, x, y, z, w, k, h, d. Like we just don't run out of variables. We can go x1, x2, x3, x4 on to infinity. So we can work with giant systems without having to create new variable values. And the shorthand for this would be if I'm looking for x1, then using Cramer's rule, I would find the matrix, the determinant sub 1 over the determinant, the A, and x2 would be the determinant of A2 over determinant A, on and on and on until we get to x sub n equals the determinant A sub n over the determinant of A. And so we can just keep working our way through a system that has more variables than x, y, z. All right, so let's use Cramer's rule to get this puppy solved. First, I want to calculate the determinant of my A sub x, or in this case, I would say A sub 1. Well, that's the determinant of, I'm going to use, I keep my x2 constants or coefficients, negative 5, negative 2, and then I'm going to replace my x1 coefficients with my constant coefficients, negative 49 and 28. A sub 2, same thing, only this time I'm going to replace my constants, the coefficients of x2 with my constants. So I get 4, negative 3, negative 49, 28. And then, of course, I just want the determinant of my coefficient matrix using 4, negative 5, negative 3, and negative 2. All right, so I'm going to do these offline because I know you know how to do them now. Remember, we're going to multiply, in all these cases, the determinant of a matrix, let's say matrix M, is using A, B, positionally, A, B, C, D. We're going to multiply A times D minus C times B. So I'm going to do that with all three of these. Here we go, and I should tell you I averted or diverted a catastrophe or a near catastrophe because I had typoed and put a minus in front of this 2. It's actually a positive, which means that this is positive and this is positive. So, crisis averted, and we can solve this now. We can say, using this information, that x sub 1 equals the A1 matrix, or the A1 determinant divided by the A determinant, negative 7. And so x1 is negative 6, and that x2 is equal to negative 35 divided by negative 7, and that equals 5. So the solution to this system of equations is negative 6, 5. All right, so let's recap. We're looking at ways to solve systems of equations by using inverses and, in fact, determinants. Inverses and determinants, and we have two methods. The first is use the inverse matrix to solve a system that has been converted to a matrix equation. And then we use basic algebra and linear operations to find the matrix and multiply. The second method, Cramer's rule. So Cramer's rule is pretty famous. It feels a little bit like like you're doing hand-wavy math, but you're not. It's actually a pretty well-established technique where you can create determinants, the determinant of the variable you're looking for, over the determinant of the coefficient matrix, and a simple calculation will take you right to the solution of the system. So there you go. Solve systems using inverses and determinants.